in this lecture, I am going to discuss how a second rank property tensor transforms under a symmetry operation. So, we have already learnt a lot about symmetry, about crystals. So, if we have a crystal with certain symmetry, so crystal with certain symmetry, the crystal remains unchanged by that symmetry operation. Now, if the crystal remains unchanged by that symmetry operation, so if I had, let us say, made a property measurement, let us say electrical conductivity, with reference to some fixed axis, and then I apply the symmetry operation to the crystal and again make the same measurement with the same fixed axis, I will get the same property. So, therefore, or from here this follows that the property tensor must also remain unchanged. So, what does that mean? That if there is a transformation of the tensor T prime I j given by this tensor notation A I m A j n T m n, where T prime I j is a transformed component under coordinate transformation. So, the individual components of the tensor will remain unchanged. One can also write it in the form of matrix, that this is the transformed tensor T prime, and this transformation is done by the direction cosine matrix A times the tensor times the direction cosine matrix transpose. So, therefore, this implies that after the transformation T prime would be equal to T. That means that the property tensor has the same property, it has to have the same property. This is one important aspect. Another is regarding second rank tensors. Almost all second rank tensors property tensors are symmetric. Now, what does this mean? This basically means that in the tensor T I j component would be equal to T j I component. If I look at the components of the tensor, so if I have T 11, T 12, T 13, T 21, T 22, T 23, T 31, T 32, T 33, then the components T 12 equals T 21, T 13 equals T 31, T 23 equals T 32. Then this tensor is symmetric. In fact, you can also say that this matrix is symmetric. And a prime example of this is electrical conductivity. Now, this property, which is there for just about all second rank property tensors, it is not there for third rank property tensors, is not arising from crystal symmetry, it is arising from the underlying physics, and as such discussion on that would be beyond the scope of this course. So, we will assume that all the second rank property tensors that we are dealing with are symmetric. Now, let us consider a particular symmetry operation, and let us consider the symmetry operation of an inversion center. Now, if there is an inversion center, how does my axes transform? Let us first have a look at that. So, this is my x1, this is x2 axis, and this is x3 axis, and remember that we are dealing with Cartesian coordinates, and there is an inversion center, let us say, at the origin of these axis system. So, what will this inversion center do? It will invert the x1 axis and make it x1 prime, invert the x2 axis, x2 prime, and invert the x3 axis to x3 prime. So, what is going to happen is that we are going from coordinate system x1, x2, x3 to x1 prime, x2 prime, x3 prime. Now, what would be the direction cosine matrix for this? So, let me just elaborate this a bit. So, I have the components of the direction cosine matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So, just to remind you, A11 is the cosine of the angle between x1 prime and the axis x1. A12 is a cosine of the angle between x1 prime and x2, and so on. So, what is going to be my direction cosine matrix capital A? Let us try to figure this out now. So, cosine of the angle between x1 prime and x1, well, you can see the angle is 180 degrees or pi. So, therefore, cos of pi is minus 1, and therefore, A11 would be minus 1. Now, you look at x1 prime and the angles it makes with the x2 and x3, clearly 90 degrees, and therefore, cosine of 90 is 0. So, A12, A13 would be 0. Now, consider x2 prime. x2 prime makes an angle with the x1 axis 90 degrees, therefore, cos of 90 is 0. So, A21 is 0, but A22, x2 prime makes an angle of 180 degrees with x2, and therefore, it is cos of pi. So, A22 becomes minus 1, and then A23 will be 0. Now, look at x3 prime. x3 prime is 90 degrees with both x1 and x2, and therefore, A31 and A32 will be 0, and A33 x3 prime makes an angle of 180 degrees, cos of 180 minus 1. So, this becomes my direction cosine matrix. Now, let us transform the tensor. So, T prime, we will just use the matrices in this case, A, T, A superscript T. Now, let us we had also discussed the properties of the direction cosine matrix, and one of the properties that we had discussed was, if I look at this matrix A, what can I say about the transpose of this matrix? Clearly, if I take the transpose of this matrix, it would be the same matrix itself. Another thing that this matrix is very simple. It is actually an identity matrix multiplied by minus 1. So, I can write this as minus 1 times the identity matrix. So, now what does the transpose tensor would look like? So, T prime I can now write as minus 1 times I into the tensor times again minus 1 into I for the A transpose. Now, minus 1 into minus 1 will become plus 1. So, this will simply become I multiplied into the matrix T multiplied into the matrix I. Now, anything that you multiply into the identity matrix, the original matrix remains unchanged, and therefore, T prime equals T. What does this mean? Under inversion symmetry, the tensor remains unchanged. So, this brings us to an important point, that all second rank tensors have the intrinsic property of inversion center. So, we can say that center of inversion is intrinsic to all second rank tensors. In fact, whether the tensor is symmetric or not, it does not matter, the center of symmetry is always present. This brings us back to the Newman's principle, that the property of the crystal must include all the symmetries that are present in the crystal, and in addition to that, it can have more symmetry, and in this particular case all second rank tensors will have inversion symmetry, whether the crystal has inversion symmetry or not. Now, let us consider another symmetry operation. Let us say we have a two-fold axis along the axis x3. So, first let us figure out what should be my direction cosine matrix, what should be the new coordinates x1 prime, new axes x1 prime, x2 prime and x3 prime. So, this is my original axes x1, x2, x3, and now let us say I have here a x3 axis has a two-fold rotation axis. So, two-fold rotation axis implies a rotation of 180 degrees. So, let us rotate about the x3 axis by 180 degrees, which would take x1 to x1 prime after a rotation of 180, it will take x2 to x2 prime under 180 degree rotation. What happens to the x3 axis? Well, x3 axis just rotates about itself, and therefore, the axis x3 prime coincides with the axis x3. Now, let us try to figure out what would be the direction cosine matrix for this? So, A11, x1 prime and x1, look at the angle 180 degrees, clearly it will be minus 1, x1 prime will be 90 degrees to x2 and x3, hence the next two elements would be 0. Take now the x2 prime axis, with x1 it is 90, therefore, A21 is 0, x2 prime with x2 180 degrees, so this will become minus 1 and the next element will be 0. Similarly, the third row would simply be 0, 0, and now you can see x3 prime coincides with x3, therefore, the angle is 0 degrees and cos of 0 is 1. So, it will be a plus 1 out here. So, this becomes the direction cosine matrix. Let me write the transformation tensor. This time I am going to use the tensor notation instead of the matrix notation. T prime ij equals aim ajn tmn. This will be the transformation of the tensor. Now, let me write one of the components of this tensor. Let me expand this. So, T prime 1 1, what would that be? So, T prime 1 1, so I and j are 1, these are the free indices. So, A1m, A1n, Tmn. If I expand this, basically means I am expanding this tensor notation by using summation over m and n going from 1 to 3, m going to 1 to 3. Essentially, what I am trying to say here is summation m equals 1 to 3, summation n equals 1 to 3, A1m, A1n, Tmn. And now expanding this, writing down all the individual terms that would be there. So, let us start with m equals 1. So, when I start with m equals 1, so I will have A11 and now vary n from 1 to 3. So, this would become n is equal to 1. So, A11 and m is 1, n is 1. So, this will be T11. Next one, again this will remain the same first term A11, because m will still keep it as 1 and n will become 2. So, this will become A12, T12, third term A11, now m is 3. So, A13, T13. So, I have 3 terms I have got for value of m being 1. Now, next one we will do for m is equal to 2 and then we will do for m is equal to 3. So, I will get another 3 terms for m is equal to 2, I will get another 3 terms for m is equal to 3, total I am going to end up with 9 terms. So, let us proceed with this. For the next 3 terms, this time m is equal to 2. So, my first coefficient will become A12. Now, n is equal to 1 to begin with. So, A11, T21 plus A12, now n becomes 2. So, this will also be A12, T22. Then I have A12 and here it will become A13, T23. Now, for the last 3 sets of terms with m is equal to 3. So, A13, this will be A11, T31 plus A13, A12, T32 plus A13, A13, T33. So, I have now all the 9 terms. Looks quite cumbersome that I have to evaluate so many terms, but let us take a look at the direction cosine matrix. The direction cosine matrix, most of the terms in the direction cosine matrix are 0. So, let us see what happens to the individual terms. So, if you look at, let us say, the second term, first let me try to say, let me start with the first term that I have, A11, A11, T11. You can see that A11 is non-zero, A11 is minus 1, A11 is minus 1 again. So, this is a non-zero term. Let us look at the second term. A11 is non-zero, but A12 is 0, and therefore, this whole term goes away. So, let us delete this. In the third term, you can see A13 is 0, so this is also gone. Now, consider the second row of this. All of the 3 terms that I get, we have A12, A12, A12 and A12 in the direction cosine matrix is 0. So, next 3 terms also get deleted, they are all 0. The last 3 terms all have A13, A13 is also 0. So, the last 3 also are deleted, and what are we left with is simply T prime 1 1 equals A11, A11, T11. Now, A11 is minus 1. So, minus 1 into T11, and this is simply equal to T11. So, all this is telling me is that the T11 component remains unchanged under this transformation of a two-fold rotation. Now, let us take a look at the second diagonal term in the tensor, which is T prime 2 2. Now, T prime 2 2, I am now, let me write it as A2m, A2n, Tmn. I am not going to rewrite all the 9, this will also give me 9 terms, but then again you will see that 8 of those are 0, only 1 is left. So, we can directly, in fact, by inspection we can tell which are the terms which will be the term which will be non-zero. So, if I look at A2m, that means I look at the second row of the direction cosine matrix. So, the second row is the only non-zero term that I have is A22, and therefore, this would be A22, A22, and this will become T22, and clearly both A22 and A22 are minus 1, and therefore, T prime 22 will be equal to T22, just like T prime 1 1. In a similar fashion, you should be able to solve this, that T prime 3 3 would also be equal to T 3 3. Now, let me look at some other components, T off diagonal component. So, T prime 1 2, let us look at this. T prime 1 2 is A1m, A2n, Tmn. Again, only look for the non-zero term. So, this would be A11 and A2n, this will be A22, and this would become T12, and both of them are minus 1, and hence T prime 1 2 will also be equal to T12. So, nothing much has happened. So far the terms that we have seen, all of them have remained unchanged, T11, T22, T33, and as well as the term T12 as well. But now let us consider another off diagonal term, T prime 1 3. Now, T prime 1 3 is A11, A1m, A3n, Tmn. Now, writing only the non-zero part, this would be A11 and this would be A33, and this will become m is equal to 1, n is equal to 3. So, this will become T13. This would be A11 is minus 1 A33 is plus 1 times T13, very clearly T prime 13 is equal to minus T13. Now, this is significant that T prime 13 is equal to T13. After the transformation, the component takes up a negative value. But now remember that this is a symmetry operation and the tensor must remain unchanged. Now, how can the tensor remain unchanged? Because here I am getting these values T prime 13 is equal to T minus T13. I would suggest that pause the video for a bit and think about it. It can take only one particular value and nothing else for the tensor to remain unchanged. And the only possible value that can be taken is T13 has got to be 0. Then only the tensor will remain unchanged. In a similar fashion, let us look at the other body diagonal term T prime 23. This will be A2m, A3n, Tmn, and I think I can leave this to you to figure this out, and that T prime 23 will be equal to minus T23. Again the same thing, this implies that T23 has also to be equal for the tensor to remain unchanged. Now, I had said that all the tensor properties that I am going to discuss are symmetric tensors, which means that T12 equals T21, T13 equals T31 and T23 equals T32. This is because we are considering all second rank tensors to be symmetric. So, this is for symmetric tensor. So, what does this mean? That tensor for a crystal which has a single two-fold rotation axis, that tensor should be, and let me now write down the tensor, should be T11. Let me first write down the diagonal terms T11, T22, T33 and the off diagonal terms T12, and it is being symmetric. Therefore, instead of writing here as T21, let me write it as T12 to show that it is symmetric, and all other terms are going to be 0. So, for a crystal with a two-fold rotation axis, the tensor will have only 5 components. So, it has 5 components, out of which only 4 independent components to describe the entire tensor. Now, which crystal would have a two-fold rotation? If you go back to the earlier lectures, the crystal which would have a two-fold rotation, this would be only a two-fold rotation, would be a monoclinic crystal. So, monoclinic crystals will have the tensor with only 4 independent components. Now, monoclinic crystal, so and this two-fold rotation here, so this is basically also I can call this as this is point group 2. But there are other point groups as well which are associated with the monoclinic crystal. So, the other point groups are, if you go back, so this is point group 2. So, this is point group 2 and this is point group 2 by m, and you will notice that at the center there is inversion as well. So, what does this mean? So, because inversion is an intrinsic symmetry of the property tensor. Therefore, whether you consider the point group 2 or you consider the point group 2 by m, or in fact even if you consider the point group m, they will all have identical or the same property tensor. Before I conclude, I will leave this as an assignment for you. Why do not you start with the point group m? Put the mirror in the x1 y1 plane. So, I have x is x1, x2, x3 and the mirror is out here. So, this is my mirror. So, the mirror will reflect the x3 axis to x3 prime down, while x1 prime axis will coincide with x1 because the x1 axis is in the mirror plane, and the same is case for x2 prime. So, x1 prime makes an angle of 0 with x1, x2 prime makes an angle of 0 with x2, x3 prime makes an angle of 180 degrees with x3. Using this, show that one gets the same second rank property tensor, which means you should get the same result T11, T12 0, T12, T22 0, then I have 0 0 T33. In the next lecture, I will consider some other symmetry operations. One will look at other point groups and see how the second rank tensors change. Thank you.